Hello and welcome to this project on traffic sign classification. So in this project, we will use a convolutional neural network to build, train and test a traffic sign classification model. So as you can see here on the left side, there are different traffic signs with different classes. We'll use this dataset to create a model. We'll build this model using TensorFlow and Keras. It is a multi-class classification problem, and this model will be used to make smarter cars. So after this project, you will be able to create a multi-class classification model using deep learning, and more precisely CNN. So the steps involved to solve this problem or to create this model are: first, I'll show you how you can find the data on Kaggle and load it into your Google Colab. I'll teach you how you can connect your Google Colab with your Kaggle account. After that, we will pre-process the images in order to normalize them, in order to find the different classes of the images, and we'll visualize them. Then we will find out the mean of these images, mean of the dimension of these images, and we will resize all the images into a same size, into a same format. Then we will convert these images into a NumPy array, because we need to mathematically work on them. We need to mathematically compute them. So we'll use a NumPy array, convert them into a NumPy array and normalize them. Then the important step is to check whether the data is balanced or not. So we'll check if there is a class imbalance or not. Then we will split this data, and we'll also perform the one-hot encoding on the target variable, that is the classes. One-hot encoding is really important because it prevents the data from getting prioritized. Then we will create the model architecture. We'll see how to compile the model and then fit the model and run it for n number of epochs, or any number of epochs that you want. Then we'll plot the accuracy and the loss against each epoch. After that, we'll see how we pre-process the test data, and we'll make predictions on that test data. And the last step will be we'll visualize the original as well as the predicted labels for the test images. As this is a traffic sign classification model, this model can be used in self-driving cars, which will enable them to automatically recognize traffics. Similarly, the driver alert system, which will help the cars to protect the drivers by understanding the traffic signs around them. This project can be used in different automobile companies which are working on self-driving cars. As you all know that self-driving cars require sensors, but other than that, these models can be really helpful, as they will be able to recognize the traffic signs as well as the symbols around the both the side of the roads. Here you can see the image how this car's traffic signs are identified with this car. So let's get started and see how to build this model. So in this project, we will use CNN, that is convolutional neural network, to build, train and test a traffic sign classification model. We will be using Google Colab, as Google Colab provides high computational power and CNN needs that. We'll build this model using TensorFlow and Keras. It is a multi-class classification problem, and this model will be used to make smarter cars. So the first step would be to connect your Kaggle account to the Google Colab, because it is important. If you connect your Kaggle account to your Google Colab, it will directly download your data into your Colab notebook rather than downloading on your local machine. And we can run the data from the Google Colab only. So the first step is to connect your Kaggle account. For that, you need to go to your Kaggle account, go to the account section and create a new API token. As you can see here, my API token has been downloaded. Now you need to upload it in your Google Colab. So here I have run this command named from google.colab. We'll import files and we'll upload this here. So after running this cell, I'll get an option to upload the file. I'll choose my Kaggle key and upload it here. So here you can see that I have uploaded my Kaggle key. Now it's connected to my Kaggle account. Next, I'll have to install a Kaggle API client. So for installing a Kaggle API client, we use pip install. Let's run this and install our Kaggle API. As you can see, it's installed now. So in order to move forward, we need to set up the Kaggle using the Kaggle API. And also we need to avoid warning if there are any on the Kaggle tool startup. So these commands will create a directory named Kaggle and save that Kaggle JSON file into that directory. Also the chmod 600 will avoid a warning on Kaggle tool startup. Let's run this cell. So now we have our Kaggle account setup complete. Next we will create a new directory which will be a traffic sign dataset, as we are working on a traffic sign classification model, and we'll change our current directory to that dataset. So here you can see that it created a directory named traffic sign dataset and change our current directory to traffic sign dataset. Next we will search Kaggle for the required dataset we want. So I already know that the dataset I want is with this name, GTSRB, German traffic sign. I'll still search it on Kaggle to download a list of datasets, and I'll select the dataset I want. So we'll run this command and get a list of all the datasets. So these are the datasets that we searched on Kaggle. Now we will download this first version, that is GTSRB German traffic signs, into our Kaggle notebook. So for this we need to run this command, that is Kaggle datasets download, and this whole name of it, the reference of that dataset. Let's download this. As you can see here, the data is currently being downloaded. It's of around 612 MB. It will directly get downloaded into your Google Colab, otherwise you have to download it on your local machine. So as you can see, the data has been downloaded. So let's move forward. Now we need to unzip this data and to remove some of the unwanted files. So here you can see that I am unzipping this traffic sign dataset. Also I am removing some of the undesired files that are meta, test, train, meta.csv. I don't need these files, so I'll remove these files. So let's run this cell and unzip our data and remove the unnecessary data. So it's working currently and it's unzipping the data and removing the unnecessary files. As you can see here, it's a large data set, so it will take some time to unzip all the data here. You can see it will take some time. What we are doing, we are unzipping the data and removing all the irrelevant files. So as you can see, we have unzipped all the data and removed the unnecessary files. Now the next step would be to start creating the model. So for that, we will first install some libraries which are important for us. So for creating a model, we need to import these libraries, which are from sklearn.model selection. We'll import test train split, which will be used to split the data. We will import two categorical functions from TensorFlow, which will be used for one-hot encoding. We will import TensorFlow also. We'll import the model, that is we are using here sequential model, and the different layers that we are going to use, that are dense, flatten, dropout, conv 2D layer and maxpool 2D layers. Other than that, some important libraries such as pandas for data frame, numpy for mathematical computation, matplotlib.pyplot for visualization, matplotlib.image for reading the image, seaborn for visualization, and so on. So let's run this cell and import all the libraries that we require. So here all our libraries have been imported. So let's move forward and visualize the data we have. So here I am visualizing some of the traffic signs from the dataset, and let's see how it looks. So here are some of the images from the dataset, and as you can see here, the dimension of the images are not same for all the images. So as the size of the images are different, we have to make them equal. So we will take the mean of these images. Here I am finding out the mean of these images. So we already know that there are 43 classes in this traffic sign dataset. So I'm running a for loop from 0 to 43, that is 43 classes, and I'll take each image and find out the mean of that image, dimension 1 and dimension 2, and we'll store it. Let's run this and store the dimension of these images to find out the mean of these images. It's running right now. So we have stored this. Next we will find out the mean of these dimensions and print them out. So here we can see that 50 by 50 is the average shape for all the images. Here we can see that the dimension 1 mean is 50.32 and dimension 2 mean is 50.83. So we can conclude that 50 by 50 is the average shape. Now we will convert all these images into this shape, 50 by 50. For that I am using images an empty list. Also our label ID is an empty list. I'll reshape all these images and also store their label IDs. For this we are running a for loop here for 43 classes and storing all the images, resizing them and also their IDs also. Let's run this cell and convert these images or resize these images into the desired dimensions, that is 50 by 50, and also storing their label IDs. It's done. So the next step would be to convert these images into a NumPy array and also to normalize them. So in order to normalize an image, we will divide it by 255 because the pixel value of each image ranges from 0 to 255. So we'll divide each image by 255 to normalize them. And to convert them into array, we'll simply use the function np.array. So let's run this cell and convert our images into NumPy array and normalize them. So it's done. Similarly, we'll store the label IDs into NumPy array and we'll see the shape of it. So here we can observe that there are 39209 label IDs. Similarly, we'll print the shape of the images. So here we can see that there are 39209 images with a shape of 50:50:3. So here 3 is the channel, which means that they are colored images in RGB format. Let's move forward. Now we'll visualize the number of the classes count to find out if the data is or the balanced or not. So here we can see that data is around 2200 in each class. So we can say that the data is not imbalanced, data is balanced. We do not need to balance the data, data is already balanced. Now we'll split the data using the test train split into a ratio of 80% training data and 20% validation data. Similarly, we'll convert the training data, that will convert the label, that is which class it belongs to, into one-hot encoding using two categorical function. So one-hot encoding is important because if we don't apply one-hot encoding, the machine will prioritize it. So to avoid prioritization, we apply one-hot encoding. So we'll apply one-hot encoding on the training and the validation data, the target variable, that is yTrain categorical and yval categorical. So we've converted it. Now the most important step is to create the model architecture. So here you can see that we are defining the model architecture. I have taken conf 2D layer with a filter size of 64, kernel size of 3 by 3. We have to pass the input shape in the first layer. The activation function, I have taken it as ReLU and the padding equal to same. Similarly, you can take any number of filters, any kernel size, any activation function, and you can change the padding also. Doing this is known as hyperparameterization or hyperparameter tuning. We have also applied some of the layers like maxpool 2D layer with a pool size of 2 by 2. We have added a dropout layer. Similarly, I have again added a conf 2D layer, maxpool 2D layer and a dropout layer. After the convolutional layers are finished, we apply a flatten layer to flatten the data and pass it to the dense layer. I have applied a dropout after the dense layer, and the final layer, as you can see here, it will always contain the number of neurons as the total number of classes, which are 43 here. As it is a multi-class classification problem, we will use the activation function as softmax because softmax works on multi-class classification and gives a probability of all the classes. So let's run this cell and make this architecture. You can change this architecture according to your own requirements. You can add as many maxpool layers as you want and we can try to achieve a higher accuracy. Let's move forward. We have created the architecture. The next step would be to compile this model. So in compiling, I have used the loss as sparse categorical cross entropy. So the loss here is sparse categorical because if we use categorical cross entropy, it will not work as the data is sparse. It contains 43 classes, which is a very diverse data. So we'll use the loss as sparse categorical. We have used the optimizer as Adam and accuracy as the metrics. We'll print out the summary of this model. Let's see. So here is the summary of the model. Here you can see all the layers with their params. We have added a conv 2D layer, then the max pooling 2D layer, a dropout layer, similarly a conv 2D layer again, and so on. And the last layer with the 43 neurons because it is the final layer. So here you can see that the total params are 1035627 and all are trainable. So now next step would be to fit this model. So in order to fit this model, we'll call the fit command and pass our data. So the data we'll pass the X-train and Y-train data. I've taken epochs as 50. You can take any size that you want. You can make this to 100, 200 or even in thousands. I've taken a batch size of 128. Still, you can change it to 256 or 512 or 1048 according to your own requirements. We have already splitted the data for the validation. So we are passing the validation data here as XVAL and YVAL. And verbose is to print the outputs of how the machine is learning on each epoch. It will take some time because I am running it on 50 epoch. Let's see how much time it takes. We'll run this command and start the training of the machine. So as you can see here, a model is getting trained. It's currently running on the first epoch and it will take time because CNN generally takes time. As you can see here, we have like so many layers. It depends on your computational power, how much computational power you have. If you have a high computational power, then you can run this very easily in a very less time. You can run this on GPUs, TPUs. Also, you can select GPUs and TPUs in Google Colab also. Let me show you how to do that. You go to the edit, click on the notebook settings, and you can select any hardware accelerator from here. That is a GPU or a TPU, anything that you want. So now let's fit the model and see what is the accuracy of this model on each epoch. For fitting, I am using epochs equal to 10 due to time limits because it will take a lot of time in training, as I'll show you. Also, I have taken the batch size as 128 and the validation data equal to XVAL and YVAL as we have splitted above. I've taken verbose equal to 2, which will show me the training of the model after each epoch. You can change this epoch size to as much as you want according to the computational power of your system. We'll fit this model on 10 epochs because it will take less time. You can change it to anything that you want. Let's run this cell and fit this model. So it starts running and we'll see here how much time it will take. I've already tried it, so I think it will take around 180 to 200 seconds. So I'll get back to you once it gets trained and we'll see what will be the accuracy. So it took around more than half an hour for this model to get trained on 10 epochs, and on the last epoch you can see that the accuracy for the training data is 0.92 while for the validated data is 0.994. So you can increase the number of epochs as much as you want if it supports your computational power. It took me around 35 to 36 minutes to run this on 10 epochs. You can change it according to your needs. So now let's see how to create the plot for the accuracy and the loss. So here what I have done is I have taken the model history and stored it into a data frame. And from this data frame, I am creating a plot of accuracy and validation accuracy. Similarly, a plot of loss and the validation loss. This is a really easy method to plot. It doesn't require any visualization library. The plot function is already predefined in the data frames in pandas. So let's plot this. So here we can see that the accuracy for the training data, and the orange line here you can see this is the validation accuracy. Shows a high gap which shows that the model is highly overfitted. You can hyperparameter tune this model in order to reduce this overfitting. Some of the techniques that you can apply are regularization of type L1 or L2, or you can apply dropouts. You can totally change this model according to your own requirements. You can change the number of layers, the number of kernels, and all that. Similarly, here you can see that the loss is decreasing for both training and the validation part. Next, let's set the variable which has the path of the dataset. As we downloaded the dataset, we found out that there is a file named gt-final-test-csv, and which is not required as it will not be processed in the images folder. So I'm removing that, and also I'm setting the test path as the traffic sign dataset test. Let's run this command and remove the unnecessary file and setting the path. So it's done. Now we'll scale these images. So why we need to scale these images? Because we need to make the test images same as the train images. So we need to scale this using a function named scaling. I have created a function here, scaling, in which we will pass the test images and the test path. I've created an empty list named images, and in the image path I have passed the test images. Now I am opening these images, resizing them into 50 by 50 and storing them as a NumPy array and appending them in the images. Similarly, these images are further converted into a NumPy array and divided by 255 in order to normalize them. And in the end, this function returns these images. I have imported a new library here. As you can see, from PIL I have imported image, and this image function is used to open these images. Let's run this function. So we have created the function. Now we will call this function using our test data, and we'll scale our test images and stored in the test images variable. So as you can see here, currently our test images are being normalized and converted into a NumPy array. It's done. So let's read these. So here we can see that we have read the test CSV and stored the values of the class in the yTest variable. Next, we will see the prediction. We'll use the model.predict classes on the test image. So next, we will store the classes name, the labels, into a variable named all labels, so we can use them for further prediction. I have taken these from Kaggle and stored them into a variable named all labels. As you can see here, we are storing all the labels. Let's run this and store these labels. So our labels are stored. So the important part here is now we will visualize the test image. Now let's visualize the test image. So this is the test image we have taken, and now we will make predictions on this test image. So let's print out the original label. First we will print out what is the original label for this image. For this we are calling the all labels list, and we are passing the yTest first one. Let's print this and see what is the original label. So the original label is speed limit 30 km/h. So here you can see that the label is, the image is for speed limit 30 km/h. Now let's find out the predicted label for this. Similarly, we are finding out the predicted label using the all labels pypred1. Let's see. So the predicted label is speed limit 30 km/h, which is exactly the original label. For original label, we have passed the yTest data, while for the predicted label, we have passed the ypred data, as you can see here. So we can see that our prediction is accurate here. So with this, we came to an end of this project. To conclude, we can say that we started with downloading the dataset. We pre-process it. In pre-processing, we see how we can convert the data into a NumPy array and normalize it by dividing it by 255. After that, we created the model. We applied different layers, conv 2D layers, max pooling 2D layers. You can change those layers according to you. After that, we make out some predictions on this model, and we found out that the predictions we done are accurate. So during pre-processing, we found out that this dataset has 43 classes. The model reached an accuracy of 95% plus in just 50 epochs. I have trained this model again and again on different parameters to optimize it. You can also do that. You just need to hyperparameter tune this model and reach a higher accuracy. Also, we saw that this model is showing some overfitting. So in order to reduce the overfitting, you can go for dropouts and regularization. You can check out the Keras documentation for dropouts and regularization to apply that. The scope of this project is that this model can be used in self-driving cars, which will enable them to automatically recognize traffic signs. Similarly, the driver alert system, which alerts the driver inside the car and will help them and protect them by understanding the traffic signs around them. Thank you.